So what we're going to do this morning is wrap up. We'll look at your plots for the two generators. We're going to look at the definition of mean or average life and the definition for specific activity. Production of isotopes. James is going to cover that in his radiopharmacy. Okay, although some of the things that we would be doing here is going to be repeated, but with regards to production, that's going to be an element of James's course. And then we'll start in with particle photon interaction mechanisms with matter, and we'll start with particle interactions. All right, I see that your file has dropped into my mailbox. Okay, I'm going to make this a little bigger. All right, okay, so what have we got here? Let's see. So you've got, all right, you want to step me through this spreadsheet?
Sure. So probably the germanium gallium one is a little simpler because I just used the simplified assumption that the germanium was one, basically. So there's just one set of numbers that are changing. And then so I just used the simplified Bateman from that section.
Okay.
And if you hover, so formula 4.26 in the book, which I unfortunately don't have my copy of the book today, George, I'm sorry.
Okay, that's all right.
If you kind of hover over, I guess the 0, you can see what function I used. So in the table, yeah, if you click that, yeah, so then that shows how I input the equation
Okay.
as per 4.26, and then
Right.
and then my little blue square shows my calculation of the decay constant,
Okay.
corrected using hours and not minutes for the half-life. Yeah, so then for germanium, I didn't input anything for that because I was just making that general assumption that the half-life was sufficiently longer than the daughter that one could just assume it was 1. So I just put in 1 for visual reasons, essentially, for my graph.
Well, that
yeah.
could be anything. It's all relative.
Yeah, yes,
Right.
and I was making that assumption as per my email that the assumption that the relative activity of the parent at time 0 was 1 and the relative activity of the daughter was 0. But yeah, so that graph I'm like relatively pleased with now that my constant is corrected.
Okay. On the basis of the graph, at what point does the activity of gallium equal germanium and stays equal?
Oh, it's essentially equal, like quite promptly, like by almost, oh, how many half-lives is that? Like 1, 2, 3, 4, by like 5 half-lives, it's almost essentially equal.
Half-lives of
gallium. So that's what I put at the bottom. The time is just increments of half-life. So 1.13 being 1 half-life, 2.26, et cetera. So by 5, 6 daughter half-lives, it's almost equivalent.
Okay. Yeah, I'll come back to this. Let's look at the molybdenum technetium 99M.
So this is the one I was struggling with a bit more. So I just graphed it twice to show like the more subtle differences, I guess, in the initial, because yeah, I just wanted more data points essentially. So that's the two graphs are just one with fewer data points and one with more data points, just to show the trend over time because I was curious. But for this one, this is when I was struggling to reflect the assumption of parent relative activity of 1 and daughter relative activity of 0 at time 0. So though I found it made sense for the daughter, I had a hard time reflecting the parent using the Bateman equation that wasn't simplified, if that makes sense, especially for technetium where the branching fraction is less. So if you go to the first table, which probably makes the most sense, and you hover again over the 0 or click on the 0.
Right here?
Yep, exactly. So that's the like non-simplified Bateman equation for the daughter there, again, using the decay constants as shown in the little blue squares. So that makes relative sense to me. I think I can understand that one. But then for the Molly, I didn't know how to input, like I didn't know how to solve for that essentially. So I used 4.27. I'm trying to recall what, if you click on the 0 for Molly, yeah, that one. So that equation, if I'm recalling correctly, it's in the section of the physics book where it's like talking about like how they should relatively decrease to one another, but there's no reflection for the activity not being, for the activity being 1 at time 0, like it doesn't account for that. It's still 0. So I was kind of dissatisfied with how that was visually represented because obviously it's starting at 0 with the technetium. So then I just used the regular, like the decay fraction equation. So if you click on where I have 1, just immediately to its right.
Okay.
So then I just used that generic equation, which shows decay of anything, but that doesn't account for the branching fraction as the prior one does, the one in C32, which you can like multiply it by the 0.875 or whatever it is, 0.9 essentially, to represent the branching fraction. So I was sort of dissatisfied with that, though it generally represents the decay of Molly. It doesn't really represent the decay of Molly with respect to the Bateman equation. So that was where my confusion arose there. So though the first equation kind of more neatly shows how they kind of end up in parallel, the latter shows like a more true decay of Molly. So anyway, so that's where my questions arose there. So then I used thank you, by the way, for your feedback. That was so kind. So in my next table, I added the equation you had recommended, which I just called Molly. And if you click on E53, the next one over, that was the additional equation you had recommended. So then I graphed that, which is remarkably similar to the one prior. You can't even tell it's another data point really, because it's the gray and the yellow and they're just entirely superimposed almost. And the numbers are quite comparable, obviously. So yeah, so it's just almost like a representation of the same thing. And then it also doesn't account for the branching fraction. So anyway, that's where my confusion arises, though there's components of both the Molly functions that make sense. I couldn't like neatly find one that represented relative activity of 1 at time 0, as well as decay with respect to the technetium, although recognizing that that's potentially of more importance. The Bateman equation is of more importance for the technetium than it is for the Molly, but there's still equations that take into the branching fraction.
Let's drill down on this. I'm going to share my screen here. And let's see, look at this. Look at Molly technetium first. Okay, can you see this?
Yeah.
Okay. So instead of 1, I used 100, but it doesn't matter, right? So this is whatever your initial activity is for your parent. This is the lambda for the parent. decay constant, and this is time in basically hours, right?
Mm.
The daughter is, so you might recall there's a term where you've got the lambda. I'm always getting that. I think it's lambda parent. No, lambda daughter divided by lambda daughter minus lambda parent.
Yeah. Yep.
Yeah. And so times the initial activity of the parent. So that boils down to, so that's 100. So that ratio, the first term, is about 1.04. So multiply by 100, and we get this for the daughter. And now that is then modified by this term, which is the difference between the daughter and the parent decay. And here's your branching fraction. And if you simplify that, that's basically 96 times each of these terms. So what I'm doing below is I'm plotting, this is the parent and this is the daughter. The daughter incorporates the branching fraction because it's being fed by the Moly 99. Not all the Moly 99 goes to technetium 99M, right?
Right.
So when we plot that, we've got this curve here, which is our molybdenum 99, and here we have our technetium. So we see that we're at, let's see here, half-life of, so if we go, this is the Moly, and that's our half-life. Moly at 50%. I don't know if you can see that. So that's about 66 hours.
Okay.
That makes sense. You see that the point at which we get a peak in the technetium curve, and then at which point it starts to follow, and we end up with a sort of a constant ratio between the two, is at about 22.6, almost 1 day. So this is what it should look like. What I noticed is that you had incorporated the branching fraction into the parent. So this is just simply, the equation of decay, radioactive decay.
Okay, so I don't.
So whatever the stated activity is on the generator, in this case, I assumed it was, 100, curies or gigabecquerels, whatever, and the decay constant, and that will always give you this curve.
Okay. Okay.
And so the daughter, this is just the Bateman equation, the general Bateman equation, and so work through. So there's a lot of terms, and it's this is why I always encourage people to use spreadsheets, because you can chunk things up and then run the calculations through. All right, let's jump to the germanium gallium, and I think you got that one. You nailed that one, and in this case, the branching fraction is 1. The other thing, as you pointed out, was the very first term. When you look at the differences between the two time constant, this doesn't really change very much, right? When you subtract this out of it in that first term. And so what you're seeing there then is this is where it can reduce to just this. You don't need to really calculate in the book. So for secular equilibrium, Terry Sorensen and Phelps shows how that's, how you can use that assumption to reduce. If you don't remember how that works, just use the Bateman equation, plug in the numbers, and you'll get an expression. So in this case, we have the plot of our germanium and our gallium, and we see that they are pretty close to 9 to 10 hours for it to come in and to get to that point where we are in secular equilibrium. So they're actually equal to each other. Let's see here with.
Should I have not used the simplified equation, George? Would you have used though it does make a big difference, it does have like a very mild degree of, like, it's not entirely horizontal. It has like a very mild slope.
Yeah, and that's because you have a half-life of about, for the germanium, of about 270 days.
Right.
And so this is, this is 240 hours or 10 days. Right. Okay. So if I extended this plot out to 270 days, we would see this even more dramatic slope.
Okay. Okay. Maybe I'll plot it again just for interest.
Yeah,
where I don't.
I think
for this one.
If you change the range of time and extend it out further, you'll see a difference. So. Okay. Instead of hours, convert the time in days and plot days, and it'll be pretty clear. So yeah, please do that.
Yeah.
Okay, so I've got a question here. So this plot gives us an idea of how often we can go to the generator to milk the gallium-68, and basically it says, we can do that every 9 to 10 hours, and the amount of gallium on hand is, once it reaches equilibrium, is going to be equal to the decay of the germanium. You agree?
Mm-hmm.
Okay. In practice, we don't see that. The amount of gallium is actually a little less than what the plot would predict. So give that some thought. What factors might in fact play into, or how would you explain that difference? And it's a real difference.
Mm-hmm. Is there a certain amount of just like impurities within whatever?
Well, no, remember, you're looking at you're looking at less gallium-68 than would be expected from the decay of germanium-68. So impurities either way wouldn't affect that.
Right, and the branching fraction is 1.
Exactly.
So that's not contributing.
Yeah, that's not going to change. And of course, we also see that same thing with technetium-99. What's predicted here is these two are related by a constant. It's obviously not 1, but the amount of technetium is a little less than the graph would predict. So sure. I'll give you a hint. There's some chemistry involved.
Uh-oh.
Think about your organic chemistry labs.
Does it like react with something and then it's no longer in its
you got to remember that in this decay where that gallium-68 is being synthesized, okay, and it's being then extracted off of a, so it's being extracted off a column, okay, ion exchange column. And so you basically, like as in the case of technetium-99m, it's saline. And what you extract is technetium-99m protectanate. So in both cases, the decay is happening on a column. You elute that column by passing saline or something equivalent through it, and you wash out. So what you're going to have is you're going to have a washout. Yes, you're going to have some impurities. So in the case of either moly-99 or germanium, some of that's going to get washed out. And we check this, and that's called breakthrough. So we check to ensure that the breakthrough is at an acceptable level. But the other thing that happens is that elution is not 100%. It doesn't pull off all of the technetium or all of the gallium-68 during the elution process. So we talk about yield, right? So this is where the chemistry comes in. So when we go down, for example, down to PET-CT, we, will generate so much activity of F18 minus. Then it goes through synthesis. It's turned into FDG, and the final product is, in that case, is going to be less than predicted because one, there is some physical decay between the F18 minus and the final FDG. It takes about 30 minutes to go through that chemical process. And in the chemistry, you lose some of that F18 minus. It doesn't turn into F18 FDG. So it's left in free form. So in the chemistry and the way everything is synthesized, there's always going to be a loss of product. So the important thing is, when you're looking at generators, and we did this for gallium, the gallium-68 generator, we looked at in practice, what is the yield? Okay, and so in some instances, the yield, is between 50 and 60%. So we're seeing, 50 to 60% less than, what's predicted. Each manufacturer has, their own yield. And in some instances, the yield will change with, the activity of the parent over time. So as the parent gets to a certain activity level, the yield changes, and that could be just the nature of the chemistry and the components of the synthesis module, that age, a lot of factors. So there's quite a bit of so that all falls into what I call the chemistry. So a lot of these generators, really the challenge is to ensure that you don't have any impurities. There isn't any breakthrough of the parent, significant breakthrough. And lastly, that the chemistry is going to be efficient and give you a very high yield.
Okay. Okay.
Can I make, is that clear or clearer?
I think so. Yes.
Yeah. Yeah. So you don't, when we draw up, so next time they're doing we're going to be doing a gallium-68 dotatate study down in PET. You'll see that a technologist will elute. Then there's a synthesis stage, and then there's, so we often prepare more gallium. We do like a bulk dose file for at least two patients given, accounting for the amount of the imaging time so that you have enough activity to pulled off of that generator to administer to those two patients that are going to be scanned in the afternoon, for example, or the three patients. So typically, we'll pull out more gallium than we actually need to account for any decay, yield. So this is, and at some point, as the generator ages, you have less flexibility because you're going to have, if we sort of look down here, we're going to have less gallium to less germanium to play with as far as, eluting the gallium.
Okay. Okay.
Okay. So give that some thought. I know James is going to come back within the radiopharmacy course. Do you know when you're taking that? Or if
It's
you
just
started?
sort of a longitudinal thing.
Okay.
Yeah. Online.
All right. Okay. Shall we leave this and move on to?
Sure.
Okay. Wonderful. I'm going to stop sharing here. All right. All right. So in your readings, do you recall this term, specific activity?
I don't know if I could define it for you, George, actually.
Okay. So really, this is, let's see here. Activity could most often megabecq per ml. So when you get, whether it's drawn off of, the moly generator and you've got technecium, or you get a predetermined kit, with iodine 131 or indium that you purchase, it's going to come in, or the FDG, it's going to come into a vial, and it's going to be diluted, 1 or 2 mils. So you're going to have so much activity in a particular volume. So when the time comes to administer the patient, this is pretty important to know, because you'll draw, the way you know how much activity that you're drawing up into the syringe is based on the, the volume you're pulling in. The technologists will always confirm that by putting the syringe into a dose calibrator to confirm that they've got the right volume. So often you'll see that as, with, say, you have a very high specific activity, something that's fresh, often what you'll see is they'll add more volume, so it's easier to draw up. And so if you're trying to drop a volume of several, drawing up a volume of several mils is a lot easier than trying to get something like, a particular activity at 0.1 cc. So when something is highly specific, there's a lot of activity, little volume, and we often dilute the content so that we have make it easier to draw up the amount of activity. So next time you're on the floor and you're administering, you'll notice that they'll have a syringe and there'll be so many ml, and they'll drop whatever the required activity is for that particular study. So in, for example, when we're doing studies with F18, so this F18 over the day is going to basically decrease. And if we didn't drop any F18 on that, the specific activity would also decrease, right? So if you were going to do a study later in the day and you were aiming for what, 10 to 15 millicuries of F18, you would end up actually having later in the day, because you've got lower specific activity, drawing up more volume to match that. Earlier in the day, you wouldn't need to drop much volume to hit this mark.
That makes sense.
Okay, does that make so the application of specific activity make sense?
It does, yeah.
Yeah, we don't deal with absolute activity really. On the floor, it's always there. The technologists are always working with specific activity, and there's nothing magical about this. When we do yttrium 90 microspheres, we do the same thing. We'll have a concentration of yttrium 90. You'll have a specific activity given by the number of yttrium 90 microspheres and the activity per microsphere. So you have a total activity divided by a particular volume. So a lot of these things are shipped with a very high specific activity, i.e. a small volume. And then depending on what you need in the day or what number of patients, then the technologist will dilute increase the volume so that you have something that is easily enough to draw and administer to the patient. Okay, enough said there. All right, let's go back to mean or average life. All right, in your readings, have you come across? So when we're looking at the absorbed dose delivered to a target organ, so when we're imaging, for example, technetium-99m and other radiopharmaceuticals, we're going to have a particular distribution. Most of it's going to go to the organ that you want to study, but they're also going to be uptake by other organs. And so when we do absorbed dose calculations, we adopt this target source model. So we look at one particular organ and we say, okay, well, what is the contribution of the neighboring organs to this? And so once something is taken up, right, there's really two ways it disappears. One, through decay, physical decay, and the other through biological excretion. So when we're trying to calculate the contribution for each of these source organs, we're going to need to know what the pattern of or rather the time history of that activity is. So typically, for a particular source organ, it's going to look like this. There's going to be an uptake, and then there's going to be a decay, which is going to be a function of both the biological half-life and the physical half-life. And we'll come to that when we do dosimetry, but essentially we're looking at time to infinity, right? So what we want to know is, how much activity is in there, and then based on the distance of that source to the target organ, the energy of the radioactive emission, we can calculate what the absorbed dose is, okay? So how do we figure this out? Well, this is where we come into this concept of average lifetime or mean. And so let's say we have a particular plot of activity, and we're looking at this at the peak here. Oh, the area under the curve we can derive, and I'm not going to ask you to do this, but that the area under this curve is equal to the area of this rectangle, where we assume that A naught and 1.44 times the physical half-life, and this could be the effective half-life, again, depending on which is longer, the biological or the physical. And so this area within this rectangle is equal to this area under this curve. So the mean or average lifetime or half-life is equal to 1.44 times the, in this case, the physical half-life. And we only use this, right? We only use this to do calculations for dosimetry, because then as long as we know what the, the half-life is and the starting activity, we don't have to do a fancy integration of the curve. We can just then substitute the initial times activity times the 1.44 or the average lifetime to get the area under the curve. So it's an approximation that simplifies the manipulation of the equations for internal dosimetry. Okay, so this is your average or mean lifetime, and how it relates to the decay. And it's always used in the context of the area under your activity curve, activity versus time.
Okay.
That's really the only place that we use that, because it approximates the area under the curve.
Okay.
When we multiply by the initial activity.
Okay.
Okay, so that's page 411. There is some discussion here of they actually derive, they derive that, right? They do integrate the curve, and they come up with this 1.44, which is so you know that the ln of 2 is natural log of 2 is 0.693, and if we take the 1 divided by the ln of 2, we get 1.44. So there's that's how they sort of get at that derivation, and that's on, you find that on the previous page here. So here, what they've done is they've integrated that curve that we just looked at from 0 to infinity. So they basically get this quantity, and you can simplify that as this, and that's equal to 1.44.
Okay.
Okay, so you need to know what the definition is and how it's different from physical half-life or biological half-life, and the context in which it's used.
Okay.
So far, so good?
So far, so good.
Okay. When we do some radiation dosimetry, we'll revisit this. But if you could remember, this plot, it's a great way to explain what's going on.
Nice.
Okay. Let's move on. So we've got this covered, and again, production, that's going to be James. And so let's look at particle interactions with matter. So when we talk about particles, what are we considering here? What are typical particles in nuke med that we're
Like
going to work
electrons and
with? Okay.
protons.
Right.
Neutrons.
Okay.
Those would be the main ones, right? Neutrinos and stuff.
What's that? Alpha particles.
Alpha, okay.
All right. So so this breaks down to, we're looking at beta minus, beta plus. So the beta minus, beta plus, the beta plus is
Like positron.
interacts in matter, and we produce, 2 511 keV photons. They're technically, we refer to them as annihilation photons, as opposed to, the gammas being emitted from within the nucleus, and they're referred to as, we're talking about gamma rays or gamma photons. So they're both photons, but this, remember, this is just gives you the origin, right? Photons emitted within the atoms, electron shells are X-rays, right? Characteristic X-rays, to be specific. So we see, so we've covered off the nomenclature here. So beta minus, these are typically, we'll see in therapy. So what are the different therapies that use beta minus off the top of your head?
Oh, that use beta minus.
Think back to the chart that I had you guys make up the first class.
Oh, like I-131.
Yeah. Okay. So we also use for imaging. Okay. What else is there?
Is yttrium a beta minus?
Yeah, it's a beta emitter. We used to use P32. Y90 we use in the liver microspheres and also in craniopharyngiomas, where it's in a colloid citrate form. Okay. And we also used to use Y90 to ablate in synovitis. Gord Borg used to use this to inject into the inflamed synovium and of a knee or elbow, typically the knees, to ablate. Not unlike some of the other chemical sort of chemo type treatments. So Y90 is very popular. It's replaced P32, but so these are the typical ones that you'll see, at least in our nukes department. Neutrons. Neutrons. Where would we see that? Neutrons are more of a nuisance. So we'll see these as byproducts in cyclotron when we're producing F18. So during the bombardment, we're irradiating O18 with protons, and in that process, you're irradiating not only the O18 water, but the target material, the parts of the cyclotron around that, and you get what's called our neutron prompts, because they interact with the the atoms that make up the shielding, the walls of the target, and so on, as well as gamma prompts. And so the reason why I call them prompts is so when you turn off the proton beam, neutrons stop being produced, and the gammas stop being produced. So the neutrons are typically a radiation safety headache. They are, they're just, you just imagine sort of you have like a basket of ping pong balls and that you throw into a room. They just bounce all over the place. And given the energy of the neutron, you'll have different effects as far as the interaction. So this is sort of more of the context of radiation safety and protection. Alphas.
Radium.
Yeah, okay, and that's the therapy. And those are particularly interesting because of we'll find out that the particle range of the alpha particle is very short. And so if you want to be able to precisely deliver short range to the tissue you want to ablate down, that's the way to go. So we'll see these things in certain therapies, and that's one that you mentioned that we're doing here. All right, so page 63, chapter 6, Cherry, Sorensen, and Phelps. Want you to read through this. There's a lot there. Read through they start with charged particle interactions, and so I want you to read through that. And next on Tuesday next week, what we'll do is we'll work through some of the concepts behind the mechanisms to ensure that you've understood it, and then we'll if there's time, we'll start with photon interaction, but I think we're going to just spend the whole class on that by itself because it's pretty important. How does that sound?
That sounds great.
Okay, wonderful. As I mentioned before, if anything comes up, please don't hesitate to drop me an email.
Okay.
Okay.
Thank you, George.
Okay. Well, take care.